So, good morning everyone. Today I am going to talk about mostly power side channel attack and its protection in the first half, and in the second half I will try to talk about how do you build ML accelerator or whatever the AI system you build for cyber security and all, how do you build them, right. If you want to map them into FPGA, what will be the easiest way to do that, right. So, and then I also talked about once you have this ML hardware running and what kind of security risks are there when they are running on edge devices, and what are the way you can attack them and how, what is the protections on that, right. So, this power side channel primarily on the hardware side. Professor Mishra was talking about various software attack, and there the primary objective was to get access of your system, right, and then try to get this information. So, here primarily these power side channel attacks have been done on this cryptographic hardware, right. So, you know this AES and all these cryptographic algorithms, they are theoretically proven, they are very secure, right. But once you implement them in hardware, there are other information you can actually access when it is running, that it is running on the devices, and from those extra informations you can actually get the key. So, here the attacker objective is to get the secret key what was there in this AES algorithm. And you understand that, as Professor Mishra was saying, that the security community, the algorithm is known to everyone, right. What algorithm is known to everybody, knows what is happening there, only thing is not known is the key. So, the objective of the attacker is to get the key, secret key, then he can actually he can get the actual message, right, not the encrypted message. So, in today I am talking the first half of this lecture, I will talk about how to actually do this power side channel attack. I think many of you do not know, you all assume that it is possible, right. But I will try to go through the AES algorithm, and if you, I mean, how do you actually, what are the steps you should follow, so that you can actually get the key from the AES implementation running on some devices, right. So, I will first half of this talk, I will talk about on this power side channel attacks, and then what are the counter measures is has been implemented and how do you protect even those kind of against this power side channel attack, right. That will be the first 1 hour plan. So, there are various side channel attack possible. One is power, as I mentioned, that your cryptographic things are running on a device and somebody is measuring the power from some interesting point of your design and then do some analysis and they can get the key. So, remember here you can control the inputs, right. You want to encrypt some text, right. So, you can give any text as you want, right, and then you can get the output. Only thing is that you cannot get any internal information, any internal values, because you have no access to the internal component of the design, right. So, you effectively only get the output and input is on your control, and only extra information you are going to get the power, for example, in power side channel. There are many other kind of attack possible. One is fault injection, is basically try to insert some fault in your circuit, right, by either increasing the temperature somewhat so that the bit get flipped, or maybe by say some voltage, ion beams or electromagnetic fields. So, there are many way people try to change or create fault into your design, and as a result your output will be not the exact one, right. And then they know what is the encrypted, because if you run the AES or correct AES, what is the correct value will come, right. So, now you know what is the corruption and what is the correct value, and be doing some analysis you can identify the key. So, this is another way of doing this attack. Timing, as Professor Mishra was discussing in the last class, that many times our algorithms are the if else loop are not basically evenly, the number of instructions in the loop, the if branch and else branch is not the same, right. So, if you, and most of the time when you write your program, that most of the condition true most of the time, right. So, that means the number of time it goes through the if branch and else branch is not the same, right, and the number of clock cycle needed to execute the behavior if it goes through 10 if else, if loop and else loop is not the same. So, if you run for multiple number of inputs and you see the delay, the time of execution, you can guess whether the if branch happens or else will happen, because the algorithm is known to you, right. So, how many instructions there in if and how many else you know. So, that is kind of the timing attack, right. So, there are also other very sophisticated like acoustic, various kind of sounds or any noise you can actually collect from the device it is running the cryptographic algorithm. and then you can do that, and also there are cache. So, from the cache misses, number of cache replacement, all those from those values you can actually also can guess what is the key value, right. So, and electromagnetic is also is part of this, right. So, this is here also. So, these are the various way of attacking a hardware implementation of an cryptographic algorithm, but in this lecture I will primarily focus on how this powered attack happen. Okay. So, please feel free to interrupt me and ask any questions. So, this powered side channel attack, as I mentioned, you have this cipher is basically your algorithm running. You can control inputs. You can actually, this control chip can give any input clock, any frequency and everything, and you can measure the power, right, what is happening. So, this is the kind of framework. Okay. So, how do you do that, right. So, basically if I give you a implementation, what are the steps you should follow or the attacker will follow to get this cryptographic keys, right. So, these are the 4 steps effectively of the algorithm or the kind of steps the attacker should follow for this attack. The first thing is that you find the point of interest in the design. Not everything is interesting. You need to identify which point of the design or when which part of the algorithm is executing. So, I want to get the power from that part, right. So, you identify what is the point of interest for you. Then you execute the algorithm on that devices for various inputs, right. So, and then you collect the traces at that point, right, and then you basically have some selection parameter, I will talk about that, through which you can expose the key. Okay. So, these are the kind of steps we should follow. Before going into this power attack, because I am going to talk about how to do in AES and it is for 128-bit keys. I will just give brief overview what AES does. So, AES has basically rounds. Okay. So, you have basically a round which has substitute bytes or S box operation, shift row, mix column and add round key. So, this happened 10 times, right, 1, 2, 3 to 10, right. So, this is the same set of operations happening here, and before that you have this add round key. So, this is the plain text, the text you want to encrypt, right, and the key is coming here, and key is basically the thing is the secret, I want to get this value. So, what is add round key? It just does the XOR between the plain text and the key, it is just the XOR operation. Sub byte is basically you access a specific S box, the value is well known, you replace those that cipher text, it is called cipher text, with the specific value from that array, right, S box based on this value, right. So, it is basically you access, this is the access, the index of that array, and you replace that with this. I will give an example also. Then shift row is basically you have the rows, you shift them in a specific predefined value, right, either shift row by 1, 1, 2 and 3, something like this. Mix column, you multiply the column with some specific values, and then again you do the add round key, right. So, this is the kind of 4 steps or operation in one round, and this is going to happen for 10 rounds. Only in the 10 rounds one of them is not happening, is the mix column, right. This is well known algorithm, and then you get the encrypted text, and this is the reverse direction, right, the same operation in reverse direction you do. So, now what is the interesting point in this algorithm where we should do the mount the attack, so that I can get the key. So, what I will do effectively, I will basically try to measure the power, right. So, this is the kind of power trace corresponding to one text, you give one text here, plain text, and this happen, entire thing is happening, and then you get the output, and this is the kind of power trace you get for one such encryption. And you can actually see there are some specific pattern, right. So, you can see here that you have this kind of pattern, right. So, you can see that there is a fixed kind of pattern here, the same thing is happening like this, right. You can easily make out that this is basically nothing but your round 1, this is round 2 and so on. So, you will see that there will be 3 rounds, 10 rounds here, right. So, you will identify this is basically the power pattern corresponding to one round, right. So, probably I do not need to check for all rounds, I will focus only on one round, right. So, because when the same kind of operation is happening, and I will specifically be interested to in round 1, because that is where my the text is more closer to what I am sending, right. The cipher text here is just XOR with the add round key, right. So, usually the mount the attack happen in the round 1, right. So, where I do not need to look for the other rounds. Okay. So, I will basically focus on the power consumption in this. So, let us zoom this, what is when if you try to extend this, what is happening, let us see. So, this is the kind of the power traces for the 1 round or the round 1, right. And what are the operation is happening here is basically S box, then shift row, mix column and add round key. So, in a careful motivation observation, because you have to do things multiple times to identify what is your point of interest, you will see that there is a kind of spike here, right, and you can correlate that this is basically nothing but the S box operation. So, this is where the S box operation is happening and there is more power consumption is happening here. So, that will be my kind of point of interest, right. So, I will try to look into the S box operation and the power consumption corresponding to the S box operation. Okay. And you can this is basically you have to do it for multiple such traces to look at whether this is consistent or not. It is just basically for one trace or one text, or it is happening for all, right. Then we will basically see that it is basically happening for kind of all. So, this will be my point of interest, right. So, this is basically where I try to look that okay. So, I will take the entire AES, I will only look for round 1 and within the round 1 I will look for only the S box operation, clear. So, now what I will do? So, now I will run many encryption, okay, and I will try to put this in a frequency domain, frequency distribution. So, it is basically you can see that this x axis is basically the power value, right, whatever the power consumption. So, now what I am doing here is that how many for text sites say probably run for 10,000 or 20,000 plain text, okay, and I will measure that for how many such plain text the value of this power is 120. So, I found that almost 15,000 for text the value is kind of 120. So, this is the kind of number you say that there are hardly for anybody is 0, right. So, you have basically very few your power consumption is 100, for very few 100 power consumption is also 140. So, this is the kind of frequency distribution that this many traces the power consumption is this. So, this I can plot, right, just run this and I get the power and I just put it and I will get this value, right. So, this I will do, it is possible to do, right. Now, I have to find the selection function. How do I basically distinguish between something, right. So, what is happening here? So, you have the plain text and in this and that which is basically XORed with the key in this add round key, and this is your cipher text, right. So, if I have this cipher text, if I have this particular say I will just pick one of the bits of that, it is basically 8 bit, right. Let us say I take one bit of them and I will see is if I make this particular. So, I will run now again for 10,000 or 20,000 plain text, but I will make that, so let us say the LSB of that bit, right. So, I will just make that LSB equal to 1 or LSB equal to 0, right. So, rest of the bit can be arbitrary. So, you have 8 bit, so you have basically 128 bit, but I will just only make the last bit 0 or 1, I make 2 distribution, right. So, I have and then I run it. So, maybe for say 10,000 test cases, and is there a difference in the power pattern, and I found that yes. So, whenever it is 1 the power pattern is this. So, the number, so basically the maximum power is coming for say here. So, this is basically the maximum is coming here when the power may be say 115 or something, but here it is coming here, right. So, there is a completely different power pattern, it is well distinguishable, understood. So, it is basically you remember I have two set of plain text on which I am running, in which my LSB is 1 and the and another case its LSB is 0, rest of the bit is random. So, now from this power pattern, now if I see this difference, then I can actually get I can distinguish between these two power, right. So, this is basically my selection values, right. I will see how I am going to use this to do the actual attack. So far it is clear what is happening, right. Okay. So, I identify this bit which basically will make the distinguish, I will make the LSB as my selection bit. And if you put it in the frequency domain, you will see that the difference, there is a significant difference when this bit is 1 or 0, right. This is corresponding to the bit 1, this is corresponding to bit 0, the LSB, and I am seeing that there is a difference, this is the difference, okay. And there are significant difference, and that is why this was coming, right. The distribution is not same. Get the point? Yes. So, this will help me to identify the key. So, I have done my homework, I do some experiment, I figure it out which bit to track, which operation to track, and how to track. So, everything is done, now I have to do the actual attack. Okay. So, so now basically I have already done this find the points of interest in my design. I will now do this, execute the algorithm and collect the trace. So, that is something I am going to do, and let us see what I am going to do. So, this is that same AES algorithm I have already talked about. I will now show you basically what is happening in this algorithm with animations. So, your plain text is say 128 bit, and then I will or sorry, this is say 16 byte, okay, which I will put it is 4 cross 4 matrix, right. So, each of them is basically 8 bit, right, which is basically this value is there. So, I am basically make it matrix, right. This will be my row 1, this will be my row 2, right. So, this will be my row 2, this will be my row 3, and this will be my row 4, right. So, this is how I just encapsulate this text into a kind of 4 cross 4 matrix, right. So, each of them is 8 bit, and you also have the A key is also 128 bit. So, that also I can put as this matrix, right, because there are 16 location into 8, which is 128 bits, right. So, I will basically distribute my key into this is how the AES is being implemented, right. So, this is also for kind of 4 cross 4, and this add round key is doing nothing but XOR, right. This is XOR. So, this is my cipher text or this actual plain text that I am giving, and I just XOR with the key. This is secret to me, and I get this matrix where it is basically XOR of this bitwise, this location wise XOR, right. This and this I will do XOR, I will get this value, right. This and this I will do XOR, and this will come here and so on. This is how the XOR is happening. Okay. So, then you have this S box where we are going to mount the attack. So, this S box is what? So, you have this cipher text which is kind of 4 cross 4 matrix, right. And you can think about this is 16. So, I will just pick this, and this is basically so this is my actual input, right, xin, which is basically this is my x, right. So, I will basically pick one of this location value which is basically say suppose this or this, and I will XOR with this kn which is the add round key, and this value will be the index of this S box, right. This is my S box, right. So, it is basically you identify this will become the index and you get that value, whatever the value is, it is a predefined, everybody knows that, and that value will replace. So, suppose I take 9, I will go to the location 9. So, suppose this is 0, 1, 2 and so on. So, suppose this is your 9th location. So, I will do say this XOR key, say this give me say 5. So, I will go to the 5th location, whatever the value I will replace this into this, right. So, I will replace here 3. So, this is S box, right. So, you basically take the plain text XOR with the key, whatever the value that will be the index of this S box, and from there you pick the value and put it here. Okay, this is S box. And this shift row is the next operation. So, this is substituted by our S box. Shift row is basically you shift the first row by nothing, right, second row by 1 bit. So, basically this will come here, this will come here, this will come here, and this will go back to here. So, it is basically shift by one location, this is shift by 2 location and so on, right. and mixed column is basically you take this column and multiply with this column, right, and then you store back into the ciphertext. Okay, this is the operation. Okay. So, but we are interested more on this, right, because this is where I found the difference in this is sub byte operation. This is what I already talked about. So, I have already identified. So, what I am going to do now? So, yeah, so the same thing is explained here again. So, you have this x n is the plain text which is the known to you, right. This is unknown or secret, and this is also unknown. Unknown because you cannot access this value, this is some internal values, right, you cannot access it, but I can control this, right, and I am objective to get the secret. So, what I will do, I will basically effectively doing this SI operation, right, you are accessing the index, right. This is what I basically say, this is known variable, this is secret and this is unknown. So, now I try to develop this algorithm, right. Can I have some tester which can identify the key, right. So, if you go back here, I know this, I do not know this and I have no access to this, and I try to guess this value, right. Can I have a tester where I give this different value of this and I want to measure the power, not this one, and I can guess each k n in my key, that is giving the desired power, right. So, this is the kind of tester, understood. So, this kind of algorithm I need to develop, right. So, I need to develop this particular algorithm. Can just I give some one key and I will do this power analysis and tell me whether this key is the correct key or not, right. And you remember, I just tell that if this is the correct key, what will happen? If you give that LSB 0 and LSB 1, that should give you two different power pattern, right. So, that is the kind of differentiator. So, so your key value, if it can give you that differentiator, then I can say that this is the correct key, right. So, how many combination you will have? You remember that if you go back here, so this is your key. So, you have basically 16 location, but I can do independently, right, each of them is 8 bit. So, this is 8 bits and there are 16, right. So, effectively for that 8 bits there can be 256 combination, right, 2 to the power 8. I will at most to identify this key, I have to try 256 values, right, and I have to try such 16 times, then I will get the entire key, right. So, this is the idea. So, effectively you have to do the entire thing for at most kind of 4096 times to get the entire key, right. So, this is what basically been done. So, what I am going to do now, this is now kind of understood to you that I know this, I have control to this value. So, I will basically give say 10,000 or 1,000 such plain text, and I will pick a specific value to this, right. So, I will set it to say 0, then I just assume whether the key is 1, key is 2, key is 3 and so on, and then I will do this, I will access this and I will get this, but only thing is that this is not available to me, but I have the power pattern corresponding to this, right. So, what I will do, I will take this value x 1, x 2, x 3, x 4 random values and I will take a specific value, right, a specific value, and then I will get 2 and then in this I will distribute this value into 2 set for 0, this is for 0, for LSB equal to 0, for LSB equal to 1, and then I will see whether I can distinguish between them or not, right. So, if I can distinguish, then this is the key, right, that is the idea, get the point, right. So, this is exactly I am going to do, that I will basically run it, I make sure that I will just point on the LSB, I will distribute them into 2, whether it is 0 or 1, I will get 2 power pattern and I will see whether the actual thing that I have identified earlier, that actually following or not. So, if I can see that this is for 0, this is for 1, say LSB equal to 0 or 1, if they are distinguishable, then this is the key, if it is not, try the next value. and at most I have to try 256 times to get the key, right. This is the idea effectively, right. So, if I get this, then this is the key, otherwise you go to the next one, right. So, basically the same thing. So, the tester will work like this, understood. So, this is how effectively you can crack AES algorithm. It has been shown that it can be done in minutes nowadays, maybe within say few minutes you can actually given an implementation. I think Professor Mishra's lab have this facility and they can easily identify the keys for AES if it is running on FPG or anywhere, and this is the kind of overall idea. Okay. Any question here? Everybody understand this, right, the core idea?
Sir.
Yes.
So, DP stands for, here is the P stands for plain text or power?
Power. I think differential power attack.
Power.
Yeah. Yeah. Yes.
One question that this has to be an intrusive method.
Sorry.
This has to be an intrusive method. Can it be non-intrusive?
What do you mean by non-intrusive?
As in, sir, that I do not need to open the box itself, and such as we do the EM one, in that from far off we can do it. So, is it possible to do it, or
So
do I have to
here
open
you
the box?
somehow access the power when you are running the text on the device.
Sir.
You are in the physical proximity of the device and you are able to measure the power.
Right. Sir.
Okay, so if you can measure, you will get the entire trace. You will not get the only that part, right? But you entire trace, you only consider that part which is interesting to you, right? And then you do the analysis. Yeah. So that's the kind of, but it is possible in specifically for say edge devices, IoT devices, right? You can always attacker by another, and they can get the key, right?
Right. Sir.
Okay, so this is the idea effectively. So, the say for example, you are running for k equal to 101, k equal to 102, and then you found that so that is not differentiating, but whenever you are running for 103, you see the differentiation between the LSB and MSB. So, LSB equal to 0 and LSB equal to 1, and so then you say this is my key, right, not the others, and I will stop there. Whenever I get it, I will stop there. Okay. So, this is basically the first part of my talk, that how effective this power analysis kind of attack, power side channel attack happen. Okay. Yes, please use the mic.
Sir, how can we say that by making the LSB equal to 0 or 1, how we can test the keys?
So yeah, it's a good question. So, basically your LSB may not able to distinguish, right. So, then you have to take the next bit and all, right. So, effectively what you do, you make the LSB equal to 0 and other bit is arbitrary, you run for 10,000 cases and you plot the pattern, and then you make it 1 and rest the bit again random, and again pattern, you make the pattern, this plot the power pattern, and if they are distinguishable, that means this is actually distinguishing, right. It actually have an impact on the overall power. So, but your luck may not be that good that in one chance LSB is differentiating, it may be the other bits, right. So, and identifying the S box also will take time, that you have to mount the attack on the S box, not on a round key or mixed column, right. So, all those things you have to do, but I think for this kind of AES and all, these are all well known now. People only attack on the round one and S box operation, and just LSB is the differentiator kind of. Okay. For new say encryption, you have to spend some time to identify that thing. Once you done that, you have to do just this step to get that. Okay. Okay, thank you. So, this first part is done. Now, I will move to the next part. So, in this talk, I am going to talk about how to protect it. So, it does not mean that that AES is now useless, right? It will still used everywhere, right? So, how do you basically make sure that you still run the AES and people can access the power, but they cannot get the key, right. So, that is the challenge, right. So, you basically make some modification to your AES algorithm, so that the power does not depend on the key. So, its basic idea is that you have to randomize the power, the dependence between power with key, you have to break that chain, right. So, if you can do that, power is independent of the key, then you will from the power you will not get it, right. So, that is the kind of key idea, that you basically make sure that your power is not proportional to or specific to the key, right. So, you randomize this. So, and it is exactly being done, that you introduce some random number in your computation, right. So, that each operation is now randomized with the random numbers, so that your correlation with the power consumption and the key is broken. That is the overall key idea. Okay. And the technique called masking. It is a very well researched area. There are so much of work has been done. It can take maybe many hours to explain all the masking techniques. So, what I am going to do is I will tell you what is the concept of masking, and if you want to mask an AES algorithm, specifically the S box, because S box is the weak point, what are the things you should do, and then if you try to implement in software, what kind of changes needed, and if you bring into hardware, which is our of interest, what are the things you will do, right. So, these are the things I am going to cover. The core concept of masking is software version as well as the hardware version, right. So, what are the things you need to take care, so that the masked implementation power side channel is not possible. Yes, please.
Sir, by doing masking, will it increase the resource power consumption for the system?
Exactly. So, it's
like we have constant IoT devices where resource, they are constant resources. So
it's a very good question. Masking has huge overhead. Okay, I will show you today that masking on AES can have 27x area overhead. So, original masking AES may be say 100, it will become 2700. So, this much overhead is there, but in certain secure application people do not care about the overhead, they want a secure version. So, then they do not bother, they want the highest level of security, right. And then in the second half of the talk, after break, I will talk about what are the low overhead implementation, right. So, how do you protect your design with low overhead. Okay. So, it is a very good important question, that masking has security guarantee, but comes with lot of power as well as area. How do you basically balance between, say probably I do not need to protect it completely, right. So, if you make sure that people cannot break within 1 million of traces, so we are just talking about 10,000, 12,000, right. So, if you say that if you take 1 million traces still you cannot break it, it is kind of safe, right. People do not have that much of energy to go beyond that, right. So, there is kind of a trade off between the security level versus the area overhead, and you should specifically for IoT devices and all, you should have a trade off between this, right. So, in one of my talk I will go talk about that, what is the trade off and how do you basically get a good protection with less overhead, comparatively less overhead, that I will talk about. So, what is the core concept of masking? It is basically, think about that you have one x, right. So, x is your secret. So, whenever you do say x or y and the output z, so some information goes here, right. So, you basically the correlation of x comes here, right. So, what I want to do, I want to break this x into shares. Okay. What I am going to do, let us say I want to make 2 shares. Okay. So, what I will do, I will take one random variable r and I will do x XOR r, that will become my share 0 or x 0, and r is my share 1. I have now 2 shares. Okay. The bottom line here is that if you somebody have access to both the share, he will get x, right, because if you have this XOR r, it will become x. So, how many shares you need effectively? Based on the assumption how many value you can trap in your design. If you say that I can have only one point I can access in the design, then 2 share is fine, because you will never get 2 value from one point, right, you will get only one value, right. So, if you basically have access to one point, I will make 2 shares, right. If I have 2 access, I will make 3 shares, so that with 2 access you will never get x, right. So, here the idea is that if you have access to both shares, you will get x. So, if I have say 2, I have to make it 3 shares, what I will do? I will do x XOR r1, this is my share 1, and then I will have r1 and then r1 XOR r2. So, I will just bring 2 random, right, and if you do XOR with all these 3, you will get x, right. So, but if you get only access to say 2 values, say basically this is for 3 share, right, this is I make it r2, this will be r2. So, if you have say, that is why I told you that this is 3 CRs, right. Original value is x, I introduce 2 random variable R1 and R2, I will create x XOR R1, that will be my input to the device now, R2 and R1 XOR R2. So, there are 3 values the input to the design, and if you have access only to say these 2 values, this and this, if you do XOR you will get this is not x, right. If you have access to say this and this, if you do XOR of this you will get this, but not x. Similarly, if you have access to this and this you will get only R1 not x, but if you have access to all 3 variables, if you XOR you will get x, right. So, based on your assumption that how many access point an attacker have, you decide how many shares you want to create for each variable. Understood? Share part is done, right. So, what else you have to do? Once you create the shares, what else you have to do now in your implementation? You have the AES implementation, right, add round key, mix column and all. What I have to do? I have to rewrite those operations in terms of now this, because I do not have x anymore, right. I have now this is say R1, this is say x0, x1 and x2. Now, I have to rewrite my entire function in terms of x0, x1 and x2, because I do not have x anymore, right. So, if I want to implement this in software, you have to rewrite the entire thing in terms of x0, x1 and x2. I will show you with examples. Okay. So, this is the same point, and this is basically an arithmetic masking. So, before going to that, this is Boolean masking, because I am assuming values are Boolean single bit, but if you have say multiple bits, the shares I will create. So, if I want to create 3 shares, this will be my share 0, this will be my share 1 and this is share 2. So, it is basically x minus R1 minus R2, x is my secret, right, x is the secret, and this may be 8 bit, it is not Boolean value anymore, right. And then I will create x minus R1 minus R2, and mod p is just to keep the value within p, right, 0 to p minus 1. And the next one is R1 and R2. Again, if you will see that if you do, you have only two value access, any 2 of them you will not get x, but if you have 3 of them you will get x. You can see that R1 crosses with this and R2 this, you will get x, right. So, this is how you, if you have your circuit is in arithmetic level, you implement this, or if you want to have a Boolean circuit, you implement this. So, this much is done, right. So, people have you do this regularly. So, then what you have to do? In software masking, you have to rewrite everything in terms of x0, x1 those shares, right. So, to give an example, suppose you have an AND operation which is A B AND of A and B. So, this was the operation in some say in original equation, right. Now, I break this A into 2 shares A0 and A1. So, where A0 is A XOR R1 and A1 is R1, B0 is again the same way, that B XOR some R2 and B1 is R2, and C0 is C1 similar way, right. There will be 2 output now instead of 1 output, because I have 2 shares, it is kind of a duplicating your circuit, right. You have to do everything on share A0. Earlier you have some computation AB, right. Now, I have to do AND operation on A0, I have to do some AND operation on A1, B0, B1, right, something like this. So, the what I will do, I will basically rewrite my operation like this. Okay. So, you do not need to go into all detail, effectively now one AND gate will become this. Okay. So, you have basically earlier A, B and C, now I have this is my AND operation, because I have share A0, B0, A0, B1, A1, B0, A1, B1, right. These are the 4 shares. So, now AND will be implemented as this, and there are this Z is another random, I will talk about bit late about this and another say 5 minutes why this Z is also needed. This is another random, okay, and this is your Y0 and Y1, and if you do XOR Y0 XOR Y1, you will get the Y, what was the actual output or C, right. So, it is basically C, the actual output. Okay. So, or say I would say this is C0, right. So, in my as per calculation this is C0, this is C1, and if you do C0 XOR C1 you will get C, the actual value that was computing earlier. So, now I think it answers your question now that how much overhead we have, right. Just one AND gate is becoming 4 AND gates plus 4 XOR gate, right. So, one gate become 8 gates, right. Earlier delay was 1, now the delay is 3, right. So, your delay will increase, your area will increase, but here nobody can get any information about A and B, because it is all things are random, right. Your A0, B0 all are random. So, there is no correlation with your secret A and B with the power consumption. So, I can guarantee that power side channel is not possible, but this is how the things will be done. Okay. So, I will now move on. So, I will now see if I have some implementation in C code, say in software level, what are the changes to be done. So, I am taking this can write S box implementation, because I want to bring this into hardware, right. So, the S box also it looks like good that you basically do S of I, right. This I is basically X I N XOR key, right. This is what you do effectively K I. But what is the size of this S box? So, this basically 8 bit, right. So, that means you can have 256 location, because 2 to the power 8. So, the S has 256 locations 0, 1, 0, 1 to 255, and each of them is basically 8 bit, right. So, it is basically 2 to the power 8, 8 into 2 to the power 8, which is basically 2 to the power 16. It is lot of area, right. So, in hardware what people do, you want to access this, but I can rewrite that in terms of function, right. So, what I will do is basically what this S box, you can think about that this is equal to y, right. You are doing this. So, what I can do, I can write all possible value of this SI, that if I equal to say this is 8 bit, right. Say 0 0 0 0 0, the output is whatever the S box value S0's value that will come, right. So, this is 1 0 1 0 something like this. So, this way if it is the value is 1, what is the value? This way I can think about what if this is 255, what is the value, right. So, now this is my y0, y1, y2 and so on, and I can just like your Carnot map minimization, I can identify what is the y0 value, what is the y0 in terms of this x0, x1 to x7, and what is y1. So, I am just giving you the idea that although it is a fixed value, but I can represent this as a function, that y0 is a function of this, y is a function of this, and then I do not need the memory, understood. So, this is what basically logically being done. Everyone understand this concept, that I do not need to make this 2 to the power 16 memory, instead I make this access Si equal to y, I know the values of this basically 0 to 255, this is also 0 to 55, I make this table and I identify what is the relation between y0 to this, right. This is what you do in your Carnot map minimization. So, once you do the hardware, nobody does this Si equal to this. So, what they do, they basically write as a function, but it is not exactly the thing I am talking about here, they make more sophisticated implementation. So, that area over it is much lesser. Okay. So, I will basically in high level I will talk about later. So, one of the function when you implement this in the for hardware, this S box using can write's idea, one of the function is basically G56 inverse, I will talk about that more detail. So, this is the kind of C code corresponding to the original implementation. Now, I want to mask it, right, and this within that you have this G16, which is another function which is calling again G, there are 4 functions, there are G4 SCL which is multiply with constant, G4 multiplier, G4 square, this will again call G2 this, and that will call a AND operation. Okay. So, this is the kind of call graph. Okay. This I will talk about what is this inverse function in a moment, right. I just give you the key idea, but the same I will see the exact implementation. So, this is your C code, you understand, right. This has this many calls, there are G16, there are 4-5 function call, each of them has a body that will call another function that will call the AND operation. Okay. So, this is the implementation. Now, if you want to mask it, what I am going to do? I now say suppose I have 2 shares, each variable becoming 2 shares. So, earlier you have this A, this will become A0 and A1, right. Suppose you have the input was x, that become x0 and x1. So, this x0 again x XOR R1 and x1 is R1, that I have already talked about. So, instead of giving x, I will now give this x0 and x1, I will do the XOR and I will give that as input. And each operation wherever I was calling say G4 mul AB, this will become now 2 function, right. So, you basically have so AB was yeah. So, let us say when this one, if I take this one, so you have this one. So, now instead of sending EB, I will send E0 U1, B0 B1, right, and output is was P. Now, I have 2 values, right, P0 and P1, 2 shares will come. So, effectively you have basically everything become double, right. If you have 2 arguments, that will become 4 arguments and so on. Everybody understand the core idea, right. So, for example, if you have this say A, now you calculate A00 and A001, right. So, you will have 2 value will calculate. Okay. So, so this is what I was talking about, that this will call this function and finally, it will call the AND operation, and this is that circuit I talked about, the implementation of AND gate, it is called DOM AND. Okay. I will talk about that in more detail. So, and then finally, why I have introduced that one more random, because this is called nonlinear gates, and nonlinear gates actually need more protection. So, they add one more random here. Okay. So, no need to go in that detail in this course, but that is the idea. So, basically if I have give you this code, I can write a tool or software that can give me this code, right. So, this is the kind of masked version of the AES, and if you run it, you do not give any power, it is not possible to do the power side channel attack. Okay. So, this was the kind of the theory, the D probing model that I talked about, that you have at most D locations of the circuit is available to you, and if you have D plus 1 shares, that is safe, right. So, if you have D probing model, you make sure that you have D plus 1 share at least. Okay. And perfect masking says that is the theoretical guarantee that any D locations, right. So, it is basically if you have the system has n location, it is kind of NCD, right. You take any possible of D from that, and that also give you give you the leak, right. So, that is the kind of theoretical guarantee, and because of that so much of overhead, right. Ideally you cannot take all possible combination, right, but theoretically you have to prove that all possible combination of D values inside values from n locations will not give you the delay, right. So, they mathematically prove those things, and I am not going to detail, and this is the kind of history. I am not again going into detail, and this is the theory. So, now I will talk about the hardware implementation. So, software part everybody understood what I did. It is basically you break into shares and rewrite your entire thing in terms of shares. Core concept is understood, right. So, no need to go into the each line of the code, understood. So, as I mentioned that this S box operations is the kind of things where you need the more protection, and then I do not want to implement that as a array, because memory it will take lot of memory. So, what they does effectively, they use some inverse affine transformation followed by a inverse table and then another affine transformation. Again I will try to not want to go into that detail what is that, but I will now try to correlate with this versus the code I have shown you earlier, right. So, what is this affine transformation is basically this A x plus c, right. This is basically is happening here, it is basically A x plus c, nothing else. And why they do this, let us skip that. And then you have the inverse table. So, again you need a table. So, they do not want that table. So, they will replace that with again that some operation. So, I do not want to this table, instead I want to do using computation, and this is the kind of computation. They break that into this and lot of equations, but finally they compute that table value using some equations. The core idea I have already shown you, right. So, finally this is your S box implementation, right. It has basically one square multiplier, this is sorry square, this is multiplication and constant multiplication, right. and then inverse GF. So, this is what I was talking about. So, what this so if you remember that I was showing this code, right. So, now you see that this square constant square multiplier inverse, this is basically these boxes, right. So, effectively this is why I show you this code, right. So, this is the kind of hardware targeted AES implementation. So, every box will see a, so this is the multiplier, right, this is the square function, this is multiply with constant, this is multiply with constant, this is square and so on. Okay. So, this is one part. So, once you try to implement in hardware, you need to replace that memory with computation, and this is the kind of things we will do. Okay. The next important point is the glitch. In the hardware, you know glitch, what is glitch? Everybody knows it? It is basically if you have two, say suppose there is an AND gate here, right. So, two values are coming. Ideally, if it is say 1 and 1, the value should be value should be 1, right. That, but say that this path is longer than this. So, this one come little bit late. So, for a moment of time there will be 0, right. This is basically there will be a moment of time there will be 0 and then there will be 1, right. So, this is glitch. So, whenever you have a circuit, not all paths are properly balanced, and there is a basically the delay of both the path is not same. So, the value will not reach at the same time, and there will be very fraction of time within the clock there will be a opposite value. What was the expected value? You will get the opposite value, and that called glitch. And in hardware, this glitch actually consume more power. So, you should try to develop circuit which has less glitch. Glitch consume dynamic powers. Okay. So, that is one side of the story. But people have shown that this glitch actually give more option for the attacker to get the key values. Okay. So, glitch actually also not safe in terms of power side channel attack. So, this glitch analysis people can identify the key, and I have one example for you. So, suppose you have some implementation where these are the shares, right, x1 and x2 is the share of one variable x, and y1 and y2 is the another share corresponding to y, and say this is the computation is happening. Now, let us say this x2 is glitchy, okay. This x2 is glitchy, that this x is coming little bit late compared to y1 and others. Okay. And if you do a thorough analysis, that they can identify that before the glitch. So, if the value of y was actually 0, the before glitch, the how many times your and this AND operation is happening here, right. So, this if you just probe here, how many times your value was 0 earlier and then what is the next value. You can see that only 2 occasions the value changes, right, sorry, up to this. If you make a line here, so in this part, this the before plus is the value just before glitch, and this is the after the glitch. So, before glitch it was 0 and then only 2 cases it is 2, right, and whenever y is 1, you see the numbers 1, 2, 4 cases it is non-zero, right. So, if you just notice the value at this point before glitch and after glitch, you can clearly say that value of y is actually 1, right. If you, the number of time, just counting the number of time the value changes before glitch and after glitch, right. So, this is basically again problematic, right. So, glitch actually can create problem and actually can give more option for the attacker to attack your circuit. Okay. So, you need to protect glitch. How do you protect the glitch? It is basically I say that there is something like this, it will basically propagate through your circuit, right. The idea is that wherever the location of the glitch, if you put a register, the glitch stops there, because values become stable there, right. So, so basic idea is that if you have normal model, if you have access to this point, you cannot guess about this, but if you have glitch, if you have access only to this, you can actually reason about this as well as the reason about this, that I have shown you what example, right. So, the protection is basically very simple, you need to put register, right. So, you have to put register. So, if you say that there is a possibility of glitch here, you put a register here. Okay. So, that is the solution. So, you need to put some register in your design to stop glitch propagation, and if you do that, that will give you the protected circuit. So, this is why this in the DOM you have this register you have to put after this cross domain computation. So, that is basically that gadget, it talks about the gadget. So, you how to basically, as I mentioned, that AND is nonlinear operation, you need more protection, and I have shown you that one case, right, that you have to move one more random here, and they say that you put another whenever you are cross domain computation. So, this is from the same domain, right, 0 is one domain and 1 is one domain. So, this is same domain, this is cross domain, this is cross domain, sorry, this is same domain, this is cross domain, because B0 A1, this is B1 A0. So, whenever there is a cross domain computation, add a random and put a register, okay, for more protection. This is theory, again why we can then there will be no leakage. Okay. And this is the final implementation of AES with DOM, and this is very low overhead. You can actually see the overhead, this is very low overhead implementation. Okay. And just before conclude, I will talk about the gadget is basically how do you implement the AND gate. I talked about this, which is basically DOM, right. So, you have basically A0 B1 and then you have A0 B1 and then this random, you put a register here and you get two output, and if you do XOR of them, you will get the actual output C, right. But there are many other gadget possible, and both have security guarantee and different. So, in literature you have HPC 2, HPC 3, then HPC 1 also is there. So, there are many gadget, and again I do not need to go into detail of them, but you can see that their area is different, number of register is different, latency is different. So, based on your, but they, the more area and more registers, the protection is more, right. So, based on your security requirement, you can pick the gadget what you need. Right. It is basically how do you replace the AND gate, you can replace by this or this. Okay. You can see here it has latency only one level, right, and one random. Here you have so many registers, but how many latency, this is one level of latency, this is another level of latency, this is another level of latency, right. So, 3 level of latency added plus so many registers, right. Here you have 2 level of latency, but register is also less, but I think there will be more random here, right. So, it is basically it has only one random, it has 2 randoms, right. So, there are 2 randoms. So, it is basically this is another direction. If you use more random generation also is costly, right. How do you generate the pure random number? So, some people want to use minimum random, but whenever you use less random, your number of register and latency will increase. So, it is a trade off again between the number of random you want to use versus number of latency you want to use in your design. Okay. So, that is a cryptographic designer job, not our job, but the core idea is this. Okay. So, that is all for now. We will have break for 30 minutes and we will come back. Then I will talk about how do you automate this process, right. So, if I give a normal AES code, how do you give me this Verilog code corresponding to this? Is it possible to generate? And if it is, then what are the things to be done and how do you get a Verilog code automatically from a AES implemented C code. So, that we will do after half an hour. Okay, thank you.